Okay, so following Wilson, we're going to be working in Euclidean space. We're going to have a momentum cutoff, and we're going to be breaking momentum space down into shells and integrating out shell by shell. Now, this might worry you a little. To understand the real world, well, in the real world, we're in Minkowski space-time. So now we work in Euclidean space with a cutoff. So can we really calculate things that we would observe in experiment? Well, in general, the answer is no, we can't. But right now, we're not trying to calculate any observables to compare to experiment. We're trying to understand quantum field theory. And it turns out that once we've understood how to work with quantum field theory in Euclidean space, that understanding will translate immediately back to Minkowski space. So don't think that we're trying to calculate anything that we'd actually measure. We're not. Euclidean space provides for us a simpler setting, a simpler laboratory in which we can study quantum field theory. And once we've understood it better, we'll be able to come back to Minkowski space and do our calculations in a more convincing way, a more careful way. And we're going to understand some nice physics from Euclidean space. Okay, so what is the quantity that we actually calculate? Well, we're going to study Z. This is the basic quantity we will study. And Z is defined to be equal to an integral over the field phi. And now I'm putting a lambda here, okay? So I'm going to have to tell you what this measure is. This is not the usual measure that you're used to. We'll define that in a minute. And then we would have e to the minus s. Good. If I wanted to calculate, say, a correlation function of some field in Euclidean space, this would be exactly this part integral that I've just introduced, e to the minus s, and I would put the fields down here in the integrand. So that looks rather similar to what we were doing before. Now let's write down what is this action S. So I'm going to work at first in 4 dimensions. Later, we will actually want to generalize this to d dimensions, but for now, it's good enough for us to work in 4. Let's put down the kinetic term. So there's a 1/2 d mu phi, d mu phi. Now, notice that both indices are written down. In Minkowski space, we always wrote one index down and one index up. When you see 2 indices down, I am giving you a little nudge in the notation to tell you that we are in Euclidean space. So this is notation to say that we are in Euclidean space, okay? Because both indices are down. Good. Okay, let's just write out this kinetic term. Okay, let's see what's the difference between Euclidean and Minkowski. I suspect you know, but no problem to write it down. So the first term will be d phi dx1, that will be squared, plus we'll have a d phi dx2 squared, d phi dx3 squared, and finally d phi dx4 squared. Okay, so all coefficients are positive. So that's a different to Minkowski. Then let's write down the mass term plus 1/2 m squared phi squared. And now it looks like the mass term has the wrong sign. In Euclidean space, we would have had a minus sign. Okay, so it's sorry, in Minkowski space, we would have had a minus sign. In Euclidean space, it's a plus sign. And the interaction also comes with a plus sign, so also unusual. I'm still going to have a phi to the 4 interaction, but I'm now going to call the coupling lambda. And calling the coupling lambda is another little notational nudge to tell you that I am working in Euclidean space. Good. So that's the action that we're going to work with. Now let me tell you what is this measure for the part integral. Our Euclidean field phi of x, okay? Now notice again, I've written phi with a vector x with an arrow on top, again to tell you this is in Euclidean space. So I'm trying to give you as many nudges as possible. In Minkowski space, we would have written x mu. So here we write x with an arrow on top. We will have an integral d4k over 2 pi to the 4. So that looks pretty similar to Minkowski. We would have phi of k, k with an arrow to again notationally nudge you towards Euclidean space, and an e to the I k dot x. Let me just make one comment that sometimes people have been asking me about. When you look at these fields, phi of x and phi of k, these are, of course, not the same function. So phi of x is one function, phi of k is a different function. It's the Fourier transform of phi of x. So why do I use the same symbol for the two, even though they're different functions? Well, I think about phi of x or phi of k as different representations of the same physical field. So it's kind of standard in our high energy community, and I guess in most of physics, to denote the field phi of x and its Fourier transform as phi of k, using the same phi. Electrical engineers and applied mathematicians, for example, would use a different name for those two functions, just explaining why our notation is the way that it is. Now, this mode expansion looks just like Minkowski. Now I'm going to add in the new feature. In fact, this integral is limited by the mod of k must be less than or equal to lambda. And this limiting is quite important. It means that if you pick if you take phi of k with the mod of k greater than lambda, that mode of the field, the mode doesn't exist, okay? So this cutoff that we're keeping here is really telling us that we only have modes up to some momentum. And that means when I do the path integral, well, integrating over all functions phi of x is equivalent to integrating over all possible modes phi of k. So the path integral measure becomes an integral over the mod of k less than or equal to lambda d phi of k. So this is what I mean by the measure that appears in my path integral defining z, and also in the path integral that I would use to define correlation functions in Euclidean space. Now, here's an important point. So let's say, what does lambda mean? Now, we've already spoken about cutoffs, okay? So certainly, Feynman, Schwinger, Tominaga, and Dyson discussed cutoffs, and they would say this is a regulator, okay? They would say that it is used to modify the theory. They would say that, in fact, it is a mathematical device that's just used to make certain infinities well defined. They would tell you, you must take lambda to infinity to get back to your original theory, and that because it's a mathematical device, they would also claim, well, this is not physical. It's just some mathematics that we're doing to define the theory. In fact, Wilson does not agree with that. Okay, so Wilson said that's not true. So in Wilson's point of view, so this is what Wilson would say. Wilson says the cutoff is a physical scale. So lambda is a physical scale. There will be some physics in nature that will tell us what the value of lambda is. We should actually be able to calculate lambda. He says quantum field theory is an effective theory. It is not fundamental, okay? Now, let's just think about what we mean by that. For example, we often talk about the fundamental forces. Friction is an example of something that's not a fundamental force. If I say to you, what are the fundamental forces, you're never going to say electromagnetism, the strong nuclear force, the weak nuclear force, gravity, and friction. Friction just isn't a fundamental force. If you think about the pen that you're writing with right now, if you were to push that pen across the table, you would feel a force of friction. So where is that force of friction coming from? Well, it's the collection of many, many atoms on the table interacting with the collection of many, many atoms in your pen. And we summarize that interaction of this enormous collection of atoms by a single force called friction. So friction is something that's phenomenological. It's some sort of an empirical model to summarize many, many fundamental interactions between the atoms that you have. And there's a limit to the description of friction. If you're studying situations like your pen being pushed across the table, you're perhaps talking about roughly Avogadro's number of atoms, so an enormous number of atoms. If you freeze it down, so you've got a clump of 1,000 atoms interacting with another clump of 1,000 atoms, well, maybe some sort of a picture of friction can be used that gives you some sort of a valid description, but we're already getting to the point where we would start to doubt whether friction holds. If we think about a single electron orbiting a nucleus, we definitely will not talk about the friction that the electron feels when it moves around the nucleus. That has got no meaning whatsoever. So friction works for big distance scales. It doesn't work for small distance scales. And that's because it's an effective theory. In the same way, quantum field theory is an effective theory, not fundamental. So QFT works down to lengths. So L must be greater than or equal to h bar over lambda, the cutoff. So that's the physical meaning of it, okay? If you want to study nature, at L less than h bar over lambda, so at even shorter distances, well, you need to add new physics. So you must add new physics. We don't know what physics you have to add, obviously, by definition of the word new. So it's unknown physics, but it would be stuff like perhaps quantum gravity, okay? So take a look at this. This is really important. Wilson is looking at quantum field theory in a very different way to the way that Feynman, Stringer, Tominaga, and Dyson viewed quantum field theory. For Wilson, quantum field theory is not fundamental. It's actually an effective theory. Good. Now, there's one other thing that I want to point out while we're here. It's well worth making this clear. And let's look at the Euclidean action. And actually, I want to rescue a few formulas here. So let's rescue these formulas down below and just discuss them a little bit. So take a look at this Euclidean action, okay? And let's just make a few comments. So this first term over here, this term over here really does look like a kinetic term. This term over here really does look like a potential term. But in Euclidean space, we're not taking the difference between them, we're adding them. So what we're calling the action actually looks like a Hamiltonian, okay? So in Euclidean space, the Euclidean action is really something more like a Hamiltonian. It's measuring an energy. And now, if you wanted to do statistical mechanics, what would you do? Well, you do a sum over all configurations. You take an e to the minus beta times by the Hamiltonian, the energy, and this is what you would call your partition function. If you were dealing with fields, the sum over configurations would become a path integral over the fields, and you would have e to the minus beta h. Well, this formula over here is now looking identical to this formula over here. Let me just make that analogy even tighter. If we were to put h bar back into this formula, we'd have e to the minus s over h bar. So s over h bar, you should be comparing to beta h, but remember that beta is 1 over the temperature. Okay, so beta is 1 over the temperature. Oh, that beta doesn't look good. That's a bit better. So beta is 1 over the temperature as usual. So we should compare this to h over beta. And we said s is completely analogous to h. So, what did I do? 1 over the temperature. We said that s is completely analogous to h. So in fact, H bar and T are equivalent. And what you can see is there's a very deep mathematical analogy. It's an exact mathematical analogy that tells you if you want to do thermal physics, thermodynamics, calculate partition functions, statistical mechanics, things like that, then the thing that's fluctuating, you have thermal fluctuations. And there's a very deep analogy in that by continuing the mathematics that we use in Minkowski space to do quantum mechanics and quantum field theory, if we continue that to Euclidean space, then we get the mathematics that's appropriate for computing thermal fluctuations. And H bar, which sets the size of the quantum fluctuations, maps into the temperature, which sets the size of the thermal fluctuations. This very deep analogy between thermal and quantum fluctuations is so far just a mathematical analogy, but this is a very exciting area where you might actually contribute something to physics by understanding the physical origin of this mathematical analogy. Good. Okay, we'll continue in a moment.